So the concept is the last one is the one of the of linear combinations. Okay, so a subspace is made of linear combinations, but it's probably it is a challenging concept. So we probably will have to do more examples of this. So once again, the meaning of linear combinations is what I'm talking about. Where are my linear combinations? This is a pretty good illustration of linear combinations. But let's just set it aside and move and try to go back a little bit, or maybe quite a bit. So here's the situation I want to suggest to you for consideration. So suppose as an example. So suppose you had two tests. Test 1, you got 0.90, and test 2, you got 0.80. What's the total?
Total what?
The score. So the what is your total for the class?
85.
Why?
You mean average or just the total?
This average total. What's your standing?
B8 or what? I can understand what you mean.
Is it depending on how many
What?
points?
What?
How many points each test was?
Right. So exactly, that's the problem. So either you don't remember, or the professor is absent-minded and didn't tell you. So, but that's where we are. You only know the two scores, and you want to figure out where you stand. Okay. So, what's your conclusion? Well, you can conclude something. Are you failing the class by any chance? No. So how do you know?
Because they're not below 70. You can't be below an 80.
Okay. Anything else? You cannot be below 80, and what?
Can't be below the 90.
Cannot be above 90. Other than that, so other than that, everything's possible. Is it? So you, what?
Convex.
No, that's all there. That's all there is. It's a made-up problem. So anything between 0.8 and 0.9 is possible.
Yeah.
Right. So all possible. Let's make it more specific, and let's suppose how you would study it. If you want to get to the bottom of it, you would just consider all possible weights. So consider all possible weights. The weights that the professor puts on these two assignments. So let's say X and Y. Okay, so then the total that you want to find will be, what is it? So it's what?
X times test 1 plus Y times test 2.
That's right. So that will be the total, and if you know X and Y, that's how you would compute the total, right? But since you don't know, what you then end up doing is you consider all possible X's and Y's. So then over, that's how I put it, over all possible X's and Y's. Okay, in other words, it's not a number anymore because the knowledge is spread out, but rather it is a set of numbers, and specifically we will discover that, or we already did, that it is an interval. Why is it an interval? Well, first of all, let's observe that this is a linear combination. Of what? Of the scores for test 1 and test 2. Okay, to begin with. It's not, well, it's also, I understand that if you had 3 tests, you would do pretty much the same thing. So once again, you have weights x, y, and z, and then you combine these x 0.9, y 0.8, and z 0.99, and that will be the linear combination of those scores. Okay. So the only thing that differs from what we have been talking about, well, first of all, it's numbers, not vectors, which is simply makes things simpler, but the idea is still the same. Second of all, the x's and y's are probably they have restrictions. They have restrictions that we do not usually have, and specifically, you would require what about the weights? Just to make the solution to this problem complete, what are the requirements on x and y? They have to add up to 100 or 1, yeah. And secondly, they have to cannot be negative. Okay, so these are restrictions that we do not have typically. When we talk about linear combinations, this is not going to appear. So the restrictions are possible. It is more like the analog would be as if we have, say, well, suppose we have two springs. Suppose there is an object and there are two springs attached to it, like this. Okay, and then you don't know how powerful those springs are. Okay, so you just know that they be being pulled in this direction or maybe the opposite direction, and then once again you might ask yourself the question in which direction you might end up being moved or the object being moved. And what do? You take the multiples of these two and combine them together in an entirely arbitrary way with no any restrictions whatsoever. Okay, so it could be here or there, all of these. So that's another kind of a real life situation that you encounter with something that does not give you as the answer a number, but rather a set of numbers. So in this particular case, a set of vectors. So all of these vectors are possible. You might be pulled in all the directions. That is all reasonable. Okay, so a linear combination of these two vectors taken together will give you a bunch of possibilities. When you talk about springs, you probably will require x and y being positive as well, but once again, in general, we don't have that restriction. Let me show you a little illustration here somewhere. Yeah, here it is. Oh, that's a big one. Oh, no, that's not the one. Here it is. Okay, so two vectors from 0 to A and from 0 to B, and then we can look at what is all convex combination. Well, that's the word that I did not use, but since we're talking about this, let's say what we're supposed to say. These are called convex combinations. Convex combinations are the ones that are linear combinations but with extra restrictions. With these extra restrictions. So they have to adapt to 1, no matter how many you've got, and they cannot be negative. So that's when you say weights. It is like you put different weights on different things, but they still adapt to 1, and they cannot be negative. So if it's like on a scale, you put weights. So that, and you look in the it is exactly like on a scale. You have 2 or more weights, and you balance them. You have weights and you distribute them along that scale. Okay, and if you look at all possible convex combinations, it's called a convex hull. Okay, and what is it in case of two vectors? It's simply all the values between those two. So that's the convex hull of A and B is this. So you see it. This is the convex hull of points A and B, including the points themselves. But it is so small because there are those restrictions. So you cannot pass B and you cannot pass A. You cannot be on the other side of 0. Let's ignore this part, but this is a linear hull. A linear hull is the set of all linear combinations. And as you can see, it is referring to the whole plane. Not only those green values that lie directly between B and B. It's like we just talked about. If you have two scores, 0.1, 0.8, 0.9, your values cannot be anywhere but between those two. And so that's the convex hull. They have to lie between A and B. Convex combinations of two vectors will lie between A and B. Okay, so these are the vectors, like this. If there are no restrictions, and that's what linear combinations are, then they will cover way more stuff. And remember, the definition of linear combination is simply sums of multiples. Okay, so for example, well, so A is a multiple, B is a multiple, and then you add them together, you're already going to have something like this vector going this way. And then if you go, this will be negative B, this will be negative A, and then all of these vectors might appear in the whole, and they cover the whole plane. So the picture is supposed to illustrate a three-dimensional situation and two vectors lying within that space. They are not multiples of each other. That's why together they produce, through their linear combinations, produce a whole plane. Okay, so that's the might help you to imagine the idea of visualize the idea of linear combinations. Algebraically, there are also examples, very simple examples of algebraic combinations. Let me just do it what I already showed them yesterday or last time. It is linear combinations of the basis vectors. So linear combinations of the standard basis vectors. So in dimension 2, it is simply I and j. Okay, so I is equal to simply 0, 1, 1, 0, and the other one is 0, 1. Okay, so if I go with AI plus BJ, I have A 1, 0 plus B 0, 1. So it gives me simply AB. Okay, so that's a linear combination of these two vectors. And look at it, it gives me any vector because I could retrace my steps and go backwards like this. Okay, so represent, that's the typical way to put it, represent vector, say 5, negative 7 as a linear combination of I and j. What's the answer? 5, negative 7 is equal to something I plus something else j. What are those numbers? 5 and negative 7, that's right. So that is very predictable, and the problem is solved. It is. We realize now that which is that we're talking about something familiar, and we just have a new angle, a new view on that idea of representing points as well as vectors in terms of the basis vectors, in terms of the components, coordinates, all that language is applicable. And it turns out if our basis vectors are chosen nicely, then the problem is solvable elementary fashion, as we just did. Right, so what are the linear combinations? Finding those two numbers A and B that we need to find, well, they've already been found. In fact, those numbers, 5 and negative 7, that is the meaning of those components. So the components 5 and negative 7 of our vectors, what is the meaning of those? They are the coefficients of a linear combination in the representation of that vector in terms of the basis vectors. Okay, so the vector is, so if these are my two vectors I and j, and my vector is 5, negative 7, 5, negative 7, made it like this, 5, negative 7. So what do? I need to have enough, I have to have I have to have a multiple of I, which turns out to be, I'm sorry, that's the multiple of I over here, so which is 5I over here, and this one is negative 7j. And my vector that I was looking for is equal to the sum of those, a multiple of I and a multiple of j. Okay, you can extrapolate into higher dimensions, doesn't make any difference. You can have three vectors in the same manner, I, j, and k, once again. So if I have a vector, a, b, c, how do I represent it in terms as a linear combination of the basis vectors I, j, and k? Well, I just put pluses. I put those components here, so I'll have A plus bj plus ck. Okay, so dimension 3. Go on, dimension Rn, same story. So you have, say, A1, A2, An. What does it mean? It means that I represent it in terms of linear combination A1, E1 plus A2, E2, An, En. Okay, so that is the meaning of those numbers to begin with. We are not, as you can see, why we're going that way, because we cannot rely on the basis vectors anymore. Because sometimes those subspaces appear out of nowhere in the form of produced from vectors that are not necessarily the standard basis vectors. So these I, j, and k, or these is vectors E1, E2, En, are so simple, and then they make our life easier. But when we are solving systems of linear equations, we end up with complex subspaces, maybe not aligned with any of the axes or coordinate axes or coordinate planes, and they might be sloped. But they're still produced by vectors, which may be might be skewed, might not be perpendicular to each other as well. In fact, perpendicularity is really not a big deal, and unless we are concerned about angles, we are concerned about dot product, the angle doesn't matter whatsoever. So let me demonstrate that. So solve the problem. Represent, say, 1, 1, vector 1, 1, as a linear combination. Let's make our life easier, and how about I take the vectors of 1, 0 and 1, 1. So this is the first one is the same, but the second one I take 1, 1. I'm sorry, what is that? Hold on a second. What is the example I was looking for? It doesn't matter. How about 3, 2? Linear combination. Oh, well, let's have 1, 1, and I'll put here, say, 4, 8. Doesn't matter. Okay. So in other words, I'm looking at so these are still my axes, x and y, but this time my basis, there are no basis vectors to worry about. This is one vector, 1, 0, and then I pick the second one, which is 1, 1. This one. So once again, in the previous example, look at it on the right. These are the two vectors ij that were the building blocks, and the solution was elementary, right? We just read off the components of our vector, and those are the coefficient. Okay, this is not going to work out anymore because, well, it's more complicated. And I have my vector 4, 3, which is maybe like something like this. So 4, 3, that's my vector v, and I need to represent that vector 4, 3 as a linear combination. So 4, 3, well, a linear combination. Let's take it. Find x and y. So I am rewriting what I've got such that the linear combination of these two vectors is our vector 4, 3. Okay? How would you proceed with this, solving this problem? What?
Y is 3 and x is
1. Oh, you're too quick. I was just trying to see what is how will we do it so that we can solve more problems in the future. What's the idea of solving the problem without guessing? Or, I don't know how he did it, but what's the method?
You can take away a 1, 0 vector until you have a multiple of 1, 1.
That is, once again, too far along the how, but rather the idea. What are we looking at? A system of linear equations. So in fact, I could write it like this: x, to take one step closer, x plus y, 1, 1, is equal to 4, 3. This is indeed a vector form of a system of linear equations. So we don't really need to invent now how to do it. We already know how, right? So that will always be applicable. Okay, so in other words, to solve this problem of representing a vector as a linear combination of other vectors, no matter what those vectors are, the problem is solved by means of solving a system of linear equations. Okay, so well, imagine that we have the vectors now are three-dimensional. So instead of 4, 3, I have, say, 4, 3, 1. And these vectors are 1, 0, 0, and 1, 1, 1, and maybe there's a third vector, 2, 3, 5. Okay, so this it still works out the same way. To solve that problem now, I have this three-dimensional vector to be represented as a linear combination of those three. How do I write it? I write it the same way: x times the first vector, 4, 3, 1, plus y. The second vector is 1, 1, 1. I'm sorry, I'm moving in the wrong direction. The first one is 1, 0, 0, 1, 1, 1, plus z. 2, 3, 5 is equal to 4, 3, 1. Solve the problem. It is a system of linear equations. You can convert it easily into augmented matrix like this and solve it. So we know how to solve it, so why worry about it? We know we can do it if we want to. Okay? So that's observation number 1 that I want to make. Finding a representation of a given vector as a linear combination, vector in Rn, let's say, as a linear combination of vectors in Rn amounts to solving a system of linear equations. Okay, so that's a very nice observation, but that's only half of what we should observe here. And that is vice versa. What's the vice versa idea? Can you convert this statement?
A system of linear equations.
What?
A system of linear equations is a linear combination.
Right, so solving a system of linear equations amounts to representing a vector as a linear combination of some other vectors. What are those vectors? They are simply the columns of our matrix. So look at what we have right there. I could go backwards like this. So to solving that system of linear equation on the right amounts to finding x, y, and z, and those x, y, and z, it's simply finding those coefficients of a linear combination. So the right-hand side, the 4, 3, 1 vector on the right, so forget about what's above, just look at this, what we have here, and we're going from right to left. So we have a system of a linear equation on the right, and so it really has nothing to do to begin with any matrices or vectors. But if we read this augmented matrix as 4 vectors present, 4 vectors, right? And then 4 three-dimensional vectors. And the fourth, the one on the right, is to be represented as a linear combination of the other 3. And then solving the system of equations or finding this representation is exactly the same thing. Okay, so it's just an interpretation, what more profound, I'd say, understanding of solving systems of linear equations is this. So we are talking about linear combinations and representing vectors as linear combinations of other vectors. Okay, so that we're gonna rely on this idea a lot, but at this time, so this kind of conversion is fairly straightforward. When you need to solve the problem exactly, you do solve it. So you might have to actually do this sometimes, but so it is the assumption that we know how to solve systems of equations, so we can at any point do it, and no trouble. Well, then probably worth mentioning that the outcomes of solving a system of linear equations might be what? We solved it, and then what can happen? What good can happen or bad can happen when you're solving a system of linear equations? What?
One answer, no answer.
Right, so no answer, one answer, or infinitely many. So don't assume that there's any difference. It's the same exact thing. So when you're trying to represent a vector as a linear combination of other vectors, the answer might be one of those. So it could be none. So you cannot represent it as a linear combination of vectors. And that is, let's illustrate that. So solution set is empty. That's the case number one. So you're trying to represent two. You have two vectors, say u and v, and then you are representing some other vector w in terms of these. How can that happen? Geometrically, can you imagine that w cannot be represented as a linear combination of u and v? That's right. That's right. So it is pointing u and v determine a plane. Okay. So these are all linear combinations, or also known as the span of u and v, or linear hull or span. It determines a plane spanned by u and v, literally spanned. That's the word is pretty descriptive. But if w is not within that plane, then you're out. If it is sticking out either totally vertically or just off, doesn't matter how. If it is not inside entirely of the plane, like this is my plane, and this vector looks like this. I cannot represent this vector in terms of vectors that within that plane, because if vectors are within the plane, I keep adding them together, they will be still lying within that plane. So that vector is out. Okay, so that's the simplest situation when you do not have the answer. Number two, one answer, one solution. Well, that's the simplest one, and that is what we assume to be the case. It is kind of natural to assume that it simply works out, and one solution. So just like with the I and j, or more vectors, there's only one way to represent vector in terms of linear combination of those. Another interesting situation is when you have infinitely many. Solutions. Can you imagine that? Three vectors, and you want to represent the third in terms of the first two. And then there is no one single answer, but there are infinitely many. Well, think like a hierarchy. This is three-dimensional. This is two-dimensional. What do you think the next one is? One-dimensional. Okay, so does that help? So the whole situation is one-dimensional. So all of these vectors, u, v, and w, lie within the same line. U, v, and w. They are multiples. Everybody's multiple of each other. So as an example, let's say And it could be multidimensional space. It doesn't matter. It doesn't have to be, it is the situation is one dimensional, but it could happen in the space of any dimension. Okay, so it just happens the vector that we're looking at, the one that provided to us, or happen to be multiples of each other in any dimensional space. So just to make that point, say u is equal to 1, 1, 1 in three-dimensional space, v is equal to 2, 2, 2, and w is equal to 3, 3, 3. Okay, so once again, I want to represent w as a linear combination of u and v. Okay, so can you give me more than one solution? Give me one. What's the first one? U plus v is equal to w. Okay, but is there another way? 2u plus 1 half v, that's right, is equal to w as well. So you have already two solutions. And you can think of many, many more in there. So indeed, there are indeed infinitely many of them. Just about anything is possible. Okay, so as you can see, everything matches. Okay, so let me give this definition to you. Well, let's go with n. We have been doing only two, but we've seen some of the higher than two, more than two vectors involved at the same time, just like with those tests that you're talking about weights of the tests, and you can have two tests, or you have three tests, or you have 50 tests. Okay, so and then you combine them together, just same thing happens here. So given vectors, u1, let's capitalize it, u2, um in Rn, a linear combination of u1, um. Once again, the definition of verbally is the same, is the sum of multiples. Doesn't matter how many of their multiples. So in other words, it will be, say, a1 u1 plus a2 u2 plus am um. It is also a vector in Rn, naturally. So remember that our vector algebra won't do anything to those vectors. They will remain vectors. So multiples, multiply still vector in Rn, and then you add them together, it's still vector in Rn. So that's the definition of a linear combination. And then additionally, the set of all linear combinations is called the span. Just in case a linear hull, since I already mentioned that, of u1, um. So a span, so when there are only two of them, like this, you are once again thinking about it's like a kite or something, and then you like create a frame like this. So you if you take the multiples of these two vectors, then and you create a what looks like a frame, and then you stretch a fabric on it like this somehow. And that creates, because the fabric is stretched tightly, it creates some kind of a plane. So I can think of, I don't know, what, tent, kite, what else? It's more interesting when dimension 3, when they have three vectors, and it is, so then the fabric doesn't work anymore. So the fabric will be still there. So if you take two at a time, there will be a bunch of stretched pieces of fabric. So if you have these three vectors, so you can still do the stretching one way, the other way like this, and the third way is like that. But that's not it, right? These are just pairwise combinations. So when it is done pairwise, you are getting only those like a two-dimensional things, stretched fabric. But then everything in between also is included. So that's how you get from the three vectors. What do you get from three vectors like this? That's right. No, not the plane, the three-dimensional space. Everything in three-dimensional space will be found this way. The only thing that can happen that prevent this from happening is when there is a dependence between the vectors. That's one more definition. So they are called, so once again, those vectors, linearly dependent. When one of them is a linear combination of the rest. It is a dependence. Okay, so imagine that these two vectors like this, they are linearly independent because you cannot express one as a linear combination of the other. When there is only, if you take one out, you're left with one vector, and you cannot, and then what's a linear combination of one vector? It's simply a multiple. And if the other vector is not a multiple of the other one, then it cannot happen. So these two are linearly independent. Okay? So linearly dependent would be multiples. So that's fairly simple for dimension 2. Dimension 3 is more complicated because yeah, the picture is here. So in other words, the last one, is there a way to solve that system of linear equations? Suppose we have three vectors. Can you express one in terms of the other two? It means that can we solve our system of linear equations like this? So is it possible that one of these is satisfied? Not number one. Number one, as you can see, W, that this one is a linearly independent set at the top, because W hovers above the plane. Okay, it cannot be expressed as linear combination of the other two. But these two they're all linearly dependent. So this is linearly independent. So once again, those definitions, what's behind them is still the same thing. It is still solving systems of linear equations. That's what linear algebra is ultimately about, how to sort out that idea of how we solve systems of linear equations with all the possible outcomes that we might not know ahead of time. Okay, so here's the definition that we had last time is here. That's the crucial definition, is a subspace. A subspace contains all of its linear combinations. That's pretty much the definition. Whether it is two or more, that does matter. That's simply the definition. So why it kind of makes sense? Because it means that we can do all the algebra. We can do all vector operations. That's what linear combinations are. It includes all possible linear vector operations that we have with those vectors. So if we have vectors u1, un, m, then multiples. That's constant multiplication, scalar multiplication, then addition. So we ask ourselves, if we start carrying out arbitrarily vector operations with these vectors, will we still stay within that, say, plane? And if we say that it is, then we have a subspace. Okay. So, but if we so it is complete in that sense. A subspace is just as good as Rn. even though it is not visible as such, because the axes are unidentified, the basis vectors are not identified, but other than that, you can, like I said, all vector algebra can be carried out. So, it's possible. So that is why I used to call them, and still makes sense, copies of Rn. We don't know, usually we don't know ahead of time what that n is. So the dimension of this subspace is to be determined, and that's what, well, once again, that's how we determine that by solving a system of linear equations. But the point is that, first of all, it is like an example of linear algebra. You could do linear algebra in Rn, or you can do it in any of these. So if we go lower dimensions, say we're talking about a plane. Let's start with a plane, and let's just look at what are the subspaces of R2. So R2 is our standard space with standard unit standard vectors, I and j. Okay, what are the subspaces? Let me tell you two right away, so they wouldn't worry about it. One is simply 0, one element. It is a subspace because 0 plus 0 multiplied by anything, it will be still 0. So there is no trouble here. And the other one, at the other end of the spectrum, it is R2 itself. Okay, so these are two trivial examples. That always works out. You take the whole thing. It is kind of degenerate. Both of them are kind of degenerate cases. The question is really anything non-trivial between them, larger than 0 but less than the whole thing. Well, one thing that we already have identified, that's the simplest example, is one of the x's. Right? So if we look at this vector, the x-axis, so the x-axis, what do the vectors look like? They look like x0. Every vector on the x-axis is x0. So suppose one is x0, and then if you try to take a bunch of these vectors and you start adding them together, subtracting, multiplying by a constant, what's going to happen? What?
You just get that vector.
Well, the point is that the second component won't change. It will be still 0. Right? So x0 plus, I don't know, x prime 0 is still equal to x plus x prime 0. So nothing is going to happen to the second component, which means that we will be staying within our within that, say, call it p, call it x. Okay, we will be staying within that subspace. So, which is how we know that it's not just a subset; it's a subspace. Okay, same with the y-axis. This one is just as good. Also, so x and y are the two main subspaces, the x's. Anything else you can think of? How about the diagonal? All the vectors are x, x. If you take the main diagonal, the two components are equal to each other. Right? Okay, so if I have x, x, and I add another one, x prime, the end result is x plus x prime, x plus x prime. So what did I just demonstrate? It is half of it. So there are two. So we have two operations, addition and scale multiplication. And what we're saying here is that they should not take us out of this space. And it didn't, right? So what is so special about this space? Here, what's so special here, x component is equal to the y component. So x component is equal to the y component. That's what characterizes elements of this say z.
Can you give an example of something that goes out of the subspace?
Right. Okay, well, it is, the thing is much easier. Because just about everything is, will take you, pick one vector, and take one vector, add it to itself, and you already taken it outside. Maybe it is an extreme example. Take a circle. One vector, another vector, add them together, out. So anything, or even just multiply it by 2, and it's out. So it has to contain at least all the multiples to begin with. That's the, in fact, probably I should have started with 1, and this is 2. So say a times xx is equal to ax. So it is still, the two components are equal to each other. Whether or not you do addition of those, or you do scalar multiplication of one vector like that, this property won't disappear. And it's very easy to think of examples that the property would disappear. So anything that is not straight, so anything kind of have any kind of curving in it, it means that they will go off, and the property will not be satisfied. So a circle, a single point, parabola, hyperbola, whatever it is, the linear algebra is really narrow in comparison to what you see elsewhere. So those are not subspaces, and there you cannot do algebra within a curve and hope to curve and hope to have still end up on the same place, in the same place. I don't know what is it. Think about motion. I guess you can try to explain this idea of linear subspaces. Motion with no forces. Motion with no forces, which means that you cannot, so you might have any velocity you want, but it's not going to change. So you will continue moving in the same direction, but, well, maybe I'm not sure that metaphor applies as well as I could. So there is nothing that would turn you away from a straight line. So that's at least. Yeah, well, I'll think of that metaphor. Anyway, so a bunch of examples which are not subspaces, but we need more subspaces. Can you find more subspaces? Well, they won't be as easy anymore, right? So we picked, these are the easy pickings. So we chose the one that were obviously the property is preserved. So y component is 0. Well, you do addition, you do scale multiplication, it will remain 0. Or the last example, they are equal to each other. Once again, they're preserved. So think geometrically. Well, the answer is every line through 0. So you can put it in a form of a theorem. All lines through 0 are the subspaces of R2. Well, let's just say in addition to zero and R2 itself. So there is no other two-dimensional space to squeeze into the two-dimensional space, for example. But every line will work. By the way, why it is not, another example, if I take a line that does not pass through the origin, like this, just take two vectors. Well, I mean, I take one vector and multiply it by 2, and it's out, right? So because, like I said, the number one thing to verify is one constant multiple, and then verify addition. Because constant multiple is just, you know, that you pick a vector, the straight line determined by that vector should be entirely contained in the subspace. Okay, so can you guess what's happening in dimension 3? The same thing plus some, because so this still holds. All line through the origin will be subspace, but there also will be planes. And they said also, once again, if the plane contains 0, it's a subspace. all lines through subgroups and only these. So there are no others, so that's crucial. Okay, so we'll just continue next.